mindsetters, welcome to a Thursday show with Looney and Cameron. How are you, Cameron?
Hi, Looney. Guys, geographers, welcome back. We've got an exciting episode today dealing with all your Mapwork calculations. Looney?
Alright, that's cool. You heard it, guys. We're doing Mapwork. So I hope you guys do enjoy the show. Don't forget to hit us up on Facebook, on facebook.com/Learn Xtra, and then on Twitter @Learn Xtra. If you're asking, Looney, but why are you holding a calculator? Well, you can win yourself this calculator just by simply completing the Taste Yourself section from the notes and then filling in the entry form. But I will post all the information on our Facebook page, guys, so don't search. Okay, so you can sign yourself to win this Casio calculator. You can download the show notes, the videos, and the schedules on learn.mindset.co.za, or you can click on the download on our Facebook page, or if you just want to view them, especially if you have a feature phone, you can view it by clicking on the link with view. Then you can view the notes. So with all that said, it's time for geography.
Guys, as Looney says, hi guys. Welcome to another exciting episode where we're going to today integrate climatology with the working of topographical maps. Today, you should be able to understand how climatology works together with Mapwork, and you should be also able to identify the integrative aspects of climate from your theory into the geographical skills and techniques on topographical maps. Let's have a closer look at what we'll be dealing with today. In today's lesson, we will be applying the following concepts. Apply skills in map reading and orthophoto maps. We will be able to analyze these in terms of climate and climatological aspects that you have studied in theory. The next one is to examine important terms as well as explain key concepts related to the locating of position. From grade 10, you have been dealing with the locating of position, which in actual fact is the calculating of the grid reference. Today we'll be analyzing the globe and how it leads to the formation of a topographic map and showing you step by step how to calculate the grid reference, or in the case of grade 10 and 11 learners, the calculating of the location of positions. Let's look further on. We will also be developing key skills in a step-by-step process in order to calculate the position on topographical maps. Further on, we will be sampling a few questions to help you practice, which is very important in the geographical skills and techniques that you use. Whenever you are answering questions, especially dealing with the calculation aspects, ensure that you practice these calculations. And today we'll be using good examples for you to better understand these calculations. And remember, always we are integrating climatology into topographical maps. And hopefully by the end of today, you will be able to identify useful hints as well as tips in applying these skills. So guys, we've got a packed show today, and hopefully by the end of today, there are two key elements that I want you to acquire. The one is to calculate the grid reference or position on a topographical map, and the other is the integration of climatology into topographical maps. Let's get straight into it. Before we go into the discussion today, I want to go back to last week's question, which was your challenge question, and also pose this week's challenge question to you. The first question that we're asking is, what is a toposcope? Hopefully you've had the past week to ensure that you've identified what is a toposcope, which was last week's question, which we will answer at the end of the show, as well as this week's question. What is the difference between a mine dump and an excavation? So guys, go quickly to the index sheet where you've got the key on your topographical maps, and you'll be able to differentiate between what is a mine dump and what is an excavation. These are your challenge questions for this week. Hopefully by the end of this lesson, we will ensure that you get the clear answers to these questions. Now, let's start off with exact position. And to do this, I'm going to call upon Looney to assist me to explain to you how we use the globe in understanding the location of position. Looney, with your help.
Okay.
So let's grab the globe. and get rid of this material here and get the globe onto the table. Now, as we've studied last week, you'll note that the Earth is geoid or spherical in shape. But I want you to zoom in onto the lines that run from east to west, as well as the lines that run from north to south. What you've learned up to this point is in your grade 10 and 11 content is the following. The lines that run from the north to the south are referred to as longitudes. The lines that run from east to west are referred to as latitudes. These are the imaginary lines which divides the Earth into hemispheres. The prime lines that you have studied at this stage is the equator, which is the 0-degree line that runs across the Earth's surface. Remember, this 0-degree line divides the Earth into a southern hemisphere and a northern hemisphere. The prime line of longitude, which is your 0-degree line of longitude, is referred to as the Greenwich meridian. The Greenwich meridian divides the Earth into a western and an eastern hemisphere. Now, when you study in grade 12 the location of position, it is this in mind that you should know the following. We have what we call the 0-degree equator. What you should understand is this is regarded as a low latitude. Any latitude, and if you look closely, there's lines of latitude, all your latitudes running from east to west across the globe or across the Earth's surface, right? The lines of latitude are referred to as follows. And note, they run across the globe. What you should remember is from 0 degrees, moving to the poles, we have up to 90 degrees. When we refer to 0 degrees, we refer to the low latitudes. 0 to 30 degrees are regarded as the low latitudes. From about 60 degrees, and now we're going to use South Africa as an example. Note, there's my equator. From 0 to 30 degrees is my low latitudes. From 30 to 60 is what we refer to as the mid-latitudes. What you should remember from your content is you study here your mid-latitude cyclone. And remember, from 60 to the poles, the South Pole in this example, is what we refer to as the high latitudes. So when we're looking at your hemispheres, note, what happens in the southern hemisphere also happens in the northern hemisphere. So you have your equator, which is your 0-degree line of latitude. From your 0-degree line, you go right up to 90 degrees. That is both in the south as well as 0 degrees, right up to 90 degrees, as well as in the northern hemisphere. As you move up, you move from the low latitudes right up to the mid-latitudes, right up to the high latitudes. This is your lines of latitude. When referring to longitudes, remember the following. Your 0-degree line of longitude is your Greenwich meridian, which runs through the town of Greenwich in England, from the northern hemisphere right down to the southern hemisphere. Remember, these lines have a north-south direction. What is important to remember, guys, is the following, is that these lines are imaginary lines. If your 0-degree line of longitude is 0 degrees, as you move from east to west in both directions, your longitudes increase as well. So these are the key elements in locating position. So what we have to do is note the following. Any position on the Earth's surface is calculated according to these lines of latitude and longitude. And in the case of South Africa, we fall south of the equator and east of the Greenwich line. Let's do that again. South of the equator, South Africa. East of the Greenwich line, which is our position. And note the following. When we refer to our position in relation to these key lines, we should note that we are between 23.5 degrees and 30 degrees south of the equator. This helps us better understand the exact position of South Africa in relation to the equator. And when we're referring to ourselves in relation to the Greenwich meridian, we are east of the Greenwich meridian. Note the Greenwich line, which runs across and down, and we are east of that line. So South Africa's position is always south of the equator and east of the Greenwich line. Looney, how was that?
Yes, that was cool.
Thanks, guys. Let's go back to the board and look at today's lesson. So, going back to what we've just discussed, let's look at a projection of the globe. Now, in grade 10, you've already understood the following. What we have here is a map that has been projected from the globe. Let's look at grid reference and a definition. A grid reference is the exact position of a point on a map given as a latitude or longitude coordinate. Now note, we've spoken about the 0 degrees as well as the 90 degrees, and between these there are many lines of latitude and longitude, each with its specific degree of either longitude or latitude. We further discussed that South Africa is always south of the equator and east of the Greenwich meridian. So, in this example, note the lines have already been drawn to indicate the equator as well as the Greenwich meridian. Note South Africa's position in relation to this line, south and east. And because of its specific location, it is given a coordinate. A coordinate is a number that is taken from these lines of latitude as well as longitude. Let's refer to some notes on this section. Latitude positions are given in degrees as a point north or south of the equator. They are lines drawn on maps horizontally that run from east to west. So what's key is in this globe that we've just looked at, we've got these imaginary lines that run from east to west, and these are referred to as latitudes. Longitude are positions given in degrees, and a point east or west of the Greenwich meridian. They are lines drawn on maps vertically that run from north to south. So in this example, we are referring to longitudes, and these run from north to south in an across direction on the globe. And each one is given a value in terms of its relation to the equator as well as the Greenwich meridian. Let's move further on. Let's look closely at South Africa. To locate places more accurately on larger scale maps, which we refer to as topographical maps, each degree is broken up into 60 minutes, and each minute is broken up into 60 seconds. Let's try and understand that better. So we have the map of South Africa in front of us, and note there's my lines of longitude, which run from north to south across the country. Note the lines of latitude running from east to west across the country. And because of these lines, each block falls within a specific block reference. These references are determined either south of the equator or east of the Greenwich line. Note the following. When we refer to 60 minutes, we're referring to the distance between any two lines of latitude or longitude. In this example, note each block that divides the northern and southern hemisphere or the eastern and western hemisphere has a distance of what we refer to as 60 minutes. Each latitude has a distance of 60 minutes. When we break these up further into its component degrees, we have a situation where these lines are divided according to its 60-minute and 60-second intervals. Now, those of you doing a subject like tourism will understand time zones. So the distance between two lines of longitude is 60 minutes, which is 1 hour. What you've studied is that as the sun moves across, you have a difference in time zones. Let's understand it in terms of the line, the distance between each line is 60 minutes, which is 1 hour. So the time difference between Durban and Cape Town, which is here, has approximately an hour to 2 hour difference depending on the number of lines that divide it. And as you move from the equator southwards, you should note that there is a time difference of 1 hour as well. What we've studied in geography is topographical maps. In grade 12, topographical maps becomes a culmination of all the map work that you've done in grade 10 and 11. And it's important to understand this concept in terms of how do we calculate position of points on a topographical map. If we look at topographical maps, you should note the following. Now, I want to draw your attention to the information on the margin of the map. In this case, you have 29 degrees and 9 minutes. This specifically refers to the lines of longitude. Note 29 degrees 9 minutes. The next line becomes 29 degrees 10 minutes, 29 degrees 11 minutes, and so on. In case of latitudes, you should note the following. It starts off in this particular case at 25 degrees 50 minutes. Note the very top line is that particular degree and minutes, followed by the next line, which is 25 degrees and 51 minutes. So you'll note that from the entire globe to the map of South Africa, to a particular map in South Africa, in this example, we've used an extract of a map. You have the breaking down of time. And in this case, we are calculating positions. So what we should remember is when we are asked to calculate a position, we are calculating a position on a map in relation to the equator as well as the Greenwich meridian. Always note the following. We give the latitude first and then the longitude, which means that our degrees has to be given in terms of south, because it's in relation to the equator, and east in relation to the Greenwich meridian. Let's look at these notes. On topographical maps, the degrees and minutes lines are indicated on the map by the grid lines. The seconds are to be calculated, which is the essence of what we're going to do today, guys. It's easily understood how to get to your degrees and minutes, and that can be extracted from the map itself, as you have seen in this example. When you have a particular point, like a trig beacon, or a contour line, or a benchmark, or a spot height on a particular topographical map, you will be required to calculate the position of that point on that map in relation to the equator as well as the Greenwich meridian. This, hopefully today, we'll be able to achieve. How's that, Looney?
Thank you, Cameron. Ready for a break?
Yes.
All right. Mindset says we are going to take a quick break, so don't go anywhere. We'll see you straight after this. Welcome back, guys, from that break. Shout out to Up Here for tuning in. Mindset is where the rest. Like, we need to be talking to all of you guys on Facebook and on Twitter. So please hit us up, guys. Don't forget to download the show notes. I did post everything on our Facebook page. Download and view for smartphones and for feature phones. If you guys have problems, we've tried to accommodate everyone. So, Cameron.
Thanks, Looney. And guys, now we're looking at specific aspects of topographical maps, higher power, and hopefully you are doing geography and you are listening to this and have a topographical map in front of you that you can analyze whilst we're using this example. Today's example is Graaff-Reinet. It's a small town that we are using in order to better understand the concept of position. Note the following. When we analyze a topographical map, especially when we're calculating the location of position or grid reference, the following aspects need to be adhered to. How to work with grid references. Let's change that pen. The latitude line forming the northern boundary of the map is. Let's have a look at the map of Graaff-Reinet. Note the following on this map. In this map, you will be able to understand the following. 32 degrees and 15 minutes is the northernmost degree of latitude. That tells us that as you move south, and note the grid lines on this map. There's my 32.15. My next line of latitude is 32.16. Let's go back to the question paper and note it's 32 degrees and 15 minutes south. So what I've done is I've been able to use the information to determine how far south is Graaff-Reinet from the equator. The longitude forming the western boundary of the map. Let's go back to our topographical map and note 24 degrees and 30 minutes. This 24 degrees and 30 minutes refers to the westernmost boundary of the map. Note the grid lines. And as you move from west to east, your grid lines will increase. So the next line is 24 degrees and 31 minutes. 24 degrees and 32 minutes. These are important aspects that you need to understand in relation to Graaff-Reinet's position to the equator as well as the Greenwich meridian. Let's go back to the question and note that, let me just check that again, 24 degrees and 30 minutes. So it's 24 degrees and 30 minutes, which is our westernmost boundary. The minutes of latitude are indicated as, let's go back to our Graaff-Reinet map and note the minute sign is different from your degree sign. When looking at these particular aspects, the signs that determine the value is important. Note how the degree sign is given as compared to the minute sign. Let's go back. The seconds are calculated for both longitude and latitude. So simply put, guys, we are able to understand how we get to degrees and minutes. The calculation of seconds gives us the exact location of that point in relation to the map. Let's have a look at an example. In this particular example, we'll be looking at the calculation of the position of a trig beacon. We've taken out an extract from one of the maps that we'll be using to understand the position, in this case, of trig beacon 97 to the equator as well as the Greenwich meridian. Note there's trig beacon 97. Note that the latitudinal position is 26 degrees and 45 minutes south. The longitudinal position is 29 degrees and 0 minutes south. The lines should be drawn according to the grids provided. Now, in order to calculate the seconds, the following steps should be taken. Always give the southern position first, which is your line of latitude. Measure the distance from the latitude directly to the north of the given place. Let's go back to the map, and you'll understand the following. If the trig beacon is located in this block, the measurement distance should be between that line of latitude and the point. Now measure the size of the latitudinal length of the grid. In this example, let's go back to our grid. It is the distance or the size between two lines of latitude. So simply put, if the distance between the line of latitude, 26 degrees and 45 minutes, and trig beacon 97 was, for example, 10 millimeters, this would be divided by the total distance between two lines of latitudes. And in this example, in most instances, standardized on topographical maps, this would be 37 millimeters. Because we are working with time, and as we've alluded to, each line has a distance of 60 seconds, which is 1 minute, and each line of longitude has a distance on a larger scale of 1 hour. When we come to topographical maps, you should note that the distance between a line of longitude, between two lines of longitude, is 60 seconds. the distance between two lines of latitude is also 60 seconds. However, note that between this line of latitude and this line of latitude, if it is 60 seconds, the trig beacon has a much shorter distance to cover in terms of time. And in this example, we've estimated it to be 10 millimeters. Note, that is the distance. The distance between two lines of latitude is 37. So what we will do, therefore, is multiply that by 60 over 1. Note the 60 seconds is in terms of the time given between two lines of latitude. 10 times 60 is 600. Divided by 37, roughly estimated, we're going to mark that as x seconds. Now note the following. I want to spend more time on the calculation. What have we done? We have taken the distance from the line of latitude to the point, which in this example is trig beacon 97. The distance between the line, which is 26 degrees and 45 minutes, and the point is roughly 10 millimeters. Once we've got that distance, which we've used a ruler to measure, we will then calculate the distance between two lines of latitude. In this example, and standardized on most topographical maps, you have a distance of 37 millimeters. Remember, we are multiplying by 60 because 60 seconds is the distance between two lines of longitude or two lines of latitude. We are currently working with the line of latitude. Note, they run from east to west. They run across the map. We're going to mark this as x. So my final calculation should note the following, and I'm going to write on this side of the board. That's 26 degrees, 45 minutes, and x seconds south. Note, my latitudinal position is given first. Now, let's move on to the longitude. When we're calculating longitude, we take into account the same procedure as for the latitude. Note the line of longitude. In this example, we are looking at trig beacon 97, which is our point, in relation to the line of longitude. We will measure the distance between the line of longitude, which is 29 degrees and 0 minutes, from that line to the point. In this example, I'm going to use the following. That this is going to be about 20 millimeters. And note, when we're calculating the distance is always 60 seconds, but in most topographical maps, we divide it by 31, which is the distance between two lines of longitude, and multiply that by 60 over 1. In this example, we've got 120 divided by 31, which we're going to give a value of y seconds. So, how do I get that y seconds? I've noticed the procedures that I've used for the latitude as well as the longitude. Note, 29 degrees and 0 minutes is my degrees and minutes of longitude, and my seconds is y seconds. Let's look at our notes. There are 60 seconds between each minute of latitude and each minute of longitude. This simply makes us better understand how to calculate the difference between two lines of latitude or two lines of longitude. When we're talking to this, we should remember that. And let's look at a map for this. In this particular map, you'll note the grid. Each grid has a specific value according to the marginal information. This information helps us better understand the location of a point in relation to the equator as well as the Greenwich meridian. Note, your 32 degrees 15 minutes is a line of latitude. It runs from east to west. Your 24 degrees 30 minutes is a line of longitude, and it runs from north to south. Any point on this particular map, for example, trig beacon 265, for example, trig beacon 87, can be calculated in relation to the equator and the Greenwich meridian in terms of its position. And what do? We look at its position in terms of the distance between the line to the top and the point, as well as the line to the left and the point. Let's go on to further examples. But before we do that, I want to now integrate some climatology into your understanding of Mapwork. So later on in the show, we're going to do a few calculations, but let's focus on some useful hints and tips to integrate climatology into Mapwork. Note the following. We will now be looking at useful hints and tips in the integration of climate and topographical maps. The rainfall in an area can be determined by the amount of natural vegetation. To simply explain this, guys, when you look at a topographical map, if it has more green features, it is a well-vegetated area. That means there's more trees, more woodlands, and this makes it a more well-vegetated area. What does this tell us? This is a high rainfall region because it supports the growth of natural vegetation. In low rainfall regions, you would expect to be low natural vegetation. The maps would have less green, as we've seen, for example, on woodlands and cultivated areas, which are reflected as green on topographical maps. The next point is, if there is less natural vegetation with non-perennial rivers, very important, little evidence of farming, the map would fall into a low rainfall region. Now, these are hints and tips to tell us the type of climatic region that the map falls in. So if we have to look at the map of Graaff-Reinet, you'll note that this northern section of the map is largely a dry region. There is little vegetation. However, we can see this particular recreational area here, as well as a boundary here. But this large region here, note the following: non-perennial river systems. Let's go a bit out of this map and try and see the rest of the map. Note, further in Graaff-Reinet, there is also further non-perennial rivers, less vegetation. As you can see, there are trees growing, represented by the green spots on the map, as well as the main road or national road, but large areas of the map are dry. So immediately we can conclude that because of the less green in the area, as well as the non-perennial rivers, note the broken blue lines on this map represent non-perennial rivers. And because of those non-perennial rivers and the less green areas on the map, we are able to conclude that Graaff-Reinet falls into a low rainfall region. The next point, if there is more natural vegetation with perennial rivers and more evidence of farming, the map would fall into a higher rainfall region. Simply, guys, this is the opposite of what we're talking about. The more green on the map means the more rainfall area that the map falls into. Graaff-Reinet is an example of low rainfall regions, mainly along the east coast, where we know that the influencing South Indian high brings in warm, moist air to the east coast, areas like Durban, as well as Port Elizabeth, where there is high rainfall regions. We would expect to find a much greener topographical map with more perennial rivers. Let's look at further hints and tips. Places further north are closer to the equator and usually have higher temperatures than places further south. This can be determined by the location of the grid reference. So, what we've been doing is understanding the position in relation to the equator. What we know is that the equator is your temperate region due to its high temperatures. As you move further south, the temperatures will decrease. Therefore, your equatorial region and further moving south, all those areas in Limpopo are regarded as high rainfall regions. Why? Because of the high levels of humidity as well as temperatures, which promote upliftment of air, creating condensation and then precipitation in the form of rainfall. So we should be able to use topographical maps that we study to determine the type of rainfall regions that we experience throughout the country. What I would expect you to know, if the area of topographical map lies on the west coast, and due to the South Atlantic high advecting cold, dry air to the west coast, you would find a much more drier region. These areas are now known for stock farming in the form of agriculture. But in the east coast, you have more crop farming in the form of sugarcane plantations as well as maize plantations. So these are hints and tips of the type of cultivated areas you will get dependent on the rainfall region that the map falls in. A further hint and tip is the following. You can use contour lines to determine altitude. Remember, your altitude is the height above sea level, and then determine the relationship between temperature and altitude. With the exception of temperature inversion, what you should note is that as you increase in height, the temperature decreases using contour lines. And we should note that the closer the contour lines is, the more steeper the slope. The more further apart they are, the more gentle the slope. So let's use a map of Graaf-Reinet to understand that. Note in this particular map, you have a situation of contour lines being close together. What we should note is that this is a steep slope all around Trigbeacon 90. However, in this region here, which is in block B2, you have a situation of contour lines being spread out. Because of the spreading out of the contour lines, it's a more gentle flat surface. Because of the closeness of the contour lines, it's a much more steeper slope. Because of the steeper slope, we should note that as you're increasing in height from the bottom flat areas towards the higher up areas, your temperature will decrease. So at Trigbeacon 90, which is Spandau Kop, you would expect a much lower temperature. Why? Because of the altitude, which is 1,315.6 meters above sea level. However, when looking at this particular area here, you find that the altitude is much lower. So we would experience a much higher temperature than when compared to this high region here. Remember that coastal locations, especially on the eastern half of the country, experience maritime climates. Now, these are key concepts which I want you to remember. The type of climates experienced along the coast is referred to as a maritime climate. Maritime refers to the sea's influence along areas of the coast. Note that along your west coast, the Cape Town area is also having a maritime climate because of the influencing mid-latitude cyclones that constantly bring rainfall to the western half of the country. However, north of Cape areas is your influencing South Atlantic high, which brings in the cold, dry air, which lowers the type of rainfall. Remember, maritime climate. In this example, in South Africa, we also experience continental climates. And in this case, we're looking at the areas of the Northwest, Gauteng, and Free State, which are largely continental climates. The differentiation between a maritime climate and a continental climate, you should note, is maritime climate refers to areas along the coastline, whereas continental climates refer to areas that are inland. Let's look at the next point. In South Africa, the north-facing slopes receive more sunlight. This can be determined by the contour lines. Now, again, I want you to note the following, that we can also test what you've done in grade 10, slope aspect, our position in relation to the equator as well as the sun. So in South Africa, all those slopes that face north or face the northern hemisphere receive more sunlight than all the slopes that face south. And in this example, if I'm looking at the map of Graaf-Reinet again, note Spandau Kop is a particular feature, and it has slopes both pointing north and south. As we've discussed last week, you should know that that is north, this is south on any topographical map. So Spandau Kop towards the B2 block is the north-facing slope, and Spandau Kop towards the C2 block is the south-facing slope. Note, there's a particular region here which is regarded as a park. So we would expect that on the north-facing slope, there would be more sunlight. On the south-facing slope, there would be less sunlight. On this particular example, B2, the block which faces north, would receive more sunlight than C2. Let's move back to the hints and tips. The prevailing wind in a valley during the day or night, and here we're referring to katabatic as well as anabatic airflows. Simply put, guys, your grade 12 content deals with valley climates. And what you've studied along this section is the aspects of anabatic and katabatic flow. Remember, anabatic is during the day, katabatic is during the night. When we look at a topographical map, we should be able to determine, according to the slope, the type of anabatic or katabatic airflow that occurs. What you should remember is anabatic flows occurs during the day and katabatic during the night. And now, before we're going to go to the calculations, I'm going to hand over to Looney for a short break.
All right. Mindset is let's take another quick break. We'll see you straight after this. Welcome back, guys, from the break. A lot of you are asking me when are the Casio winners going to be announced. Next week, we'll have Oyo winners. So all the winners from this week, we'll tell you guys next week. So make sure you watch all of the shows from next week to see if you're a winner. Come on.
Thanks, Looney. Guys, thank you for the emails and the questions. We're going to try and get one calculation done on grid referencing today with the map of Graaff-Reinet, and you will be able to understand better how we identify this information. We've also got a challenge question which we're going to answer, so hang in there. Let's look firstly at the type of question you will receive for this type of example. Refer to the topographical map. Let's get our pens in there. Refer to the topographical map of Graaff-Reinet. The first question that we'll be dealing with is the following. Calculate the position. And note always, your position is calculated in terms of its relation to the equator, which is south. We are south of the equator, and the Greenwich Meridian. We are east of the Greenwich Meridian. Of Trig Beacon in 87 in block A1. And for this example, we're going back to Graaff-Reinet. And let's go up here. And there's block A1. Note the position of Trig Beacon 87 in block A1. This is the full map. We've managed to extract this map. But what I want you to note is we're using the same degrees and minutes. So let's go back to the question and look at the map. We've managed to get an extract of this map. Our step-by-step process will lead us to the answer for degrees and minutes and seconds. Note, the degrees and minutes are read off the topographical map. The seconds are calculated. Let's go straight to the map and understand the section. So firstly, for Trig Beacon 87, I would have to draw a line from that point to the top line of latitude. Note this example, the latitude is 32 degrees and 15 minutes. Let's look at the longitude from the point to the line to the left. And in this example, note your line of longitude is 24 degrees and 30 minutes. Longitude, 24 degrees and 30 minutes. What I have to do is calculate the seconds south and the seconds east. Let's help you with that. So, what have we done? Step 1, determined the longitudinal coordinates. Step 2, determine the longitudinal coordinates. Step 3, measure. Note, when we're measuring, we're always going to measure in millimeters. This is a more accurate determination of the distance between the line and the point, between the latitude and the point. And step 4, measure again, as well as remembering that it is in millimeters, the distance between the two latitudes. I'm going to go further and check the next step. Step 5, measure again in millimeters the distance between the longitude and the point. And step 6, measure the distance between two lines of longitude. When we do this, we are able to calculate position. So simply put, guys, what you should note is that this distance is in millimeters. This distance between latitudes is in millimeters. The distance between two lines of latitude. The distance between two lines of longitude. I estimated the measurement as follows. I'm going to keep it there. For my latitude, I received 12 millimeters. That is the distance between that line and the point. Over the total distance, remember it's standardized. So always the distance between two lines of latitude, between there and there, or there and there, is always 37 millimeters. And what do we do with this? We multiply by 60 over 1. Where did I get the 60 from? Note, between each line of latitude, the distance is always 60 seconds or 1 minute. 60 seconds or 1 minute. This is the distance between two lines of latitude. When we're looking at longitudes, we should note the following. The distance between one line of longitude and the next is always the same as the latitude, which is 60 seconds, which is equivalent to 1 minute. However, the distance varies, and in this case, I want to draw to your attention the following. The distance between longitudes could be between 31 millimeters to 33 millimeters. I would advise you to always ensure that you secure the measurement of this example. Let's go back to our question. And then when we're calculating, we should note that because of this particular calculation, we should focus on the distances accurately between latitudes, between longitudes, and between latitudes and the point, and longitudes and the point. So this example will be as follows. Note, we've got 12 millimeters over 37 millimeters times 60 over 1. In this example, that's 60 times 12, and I'm going to put it as x seconds. And in this example, further, when we worked out the distance between the line of longitude and the point, we had 15 millimeters. So for the longitude, 15 over 31 millimeters times 60 over 1. And this we're going to put as y. Once we've got these two answers, x seconds and y seconds, we should go back to our original answer. And remember, your x seconds goes there and your y seconds goes there. So this is simply the procedure that you would follow in order to calculate the exact position to degrees, minutes, and seconds. I'm going to move on further to the following. Note this next example, trig beacon 91, and I'm going to quickly go through this. Remember, trig beacon 91 is in block D4. So let's go back to block D4. And in block D4, we have trig beacon 91. Note, with trig beacon 91, we will go to the top line and then across. And when we're looking at it across, we will count the number of lines. Note the line to the top. In this example is this particular line. And the line to the left in this example you'd go that way. This is how we use the procedure. We work within the block, and therefore we'll calculate 32 degrees, 51, 52, 53. Let's look at it. 32 degrees, 15, 16, 17, 18. So my latitudinal position is 32 degrees and 15, 16, 17, 18. 32 degrees and 18 minutes. For my longitudinal position, I would move to the left and this line, which is 24 degrees, 30, 31, 32, and 33. And use the same procedure to calculate the seconds. Let's move on back. Now, let's look at the key questions for this particular map in terms of climatology. Name 2 examples of visible evidence on the map that indicates this is a low rainfall area. I'm going to go to the map again of Graafrenet. Note we've discussed this particular map. Note there's an absence of green areas on this map. Because of that, you have non-perennial rivers. You also have furrows and canals, as well as storage dams. Storage dams further emphasize the point that water needs to be stored during the dry season or the lack of rainfall. So in this particular map, it is a low rainfall map. The next question. Determine the north-facing slope of Spandau Kop in blocks B2 and C2. As we've discussed previously, you should note that this area here is your north-facing slope, and this particular area is your south-facing slope. I'm going to go now to the toposcope, which is your challenge question. If you've answered it well, you should receive the following. Right, let's get there. And arrow, yes. And let's cut that out. And remember, your toposcope is the instrument used to determine the bearing of a position in relation to a topographical map. I want to quickly refer you to today's question. And what is the difference between the mine dump and an excavation? Note the following. In this example, you have the following: a mine dump and an excavation. Note the difference that a mine dump has no definite area, whereas an excavation has a particular area around it. In a topographical map, you must be able to identify the following. With that, guys, we've run out of time. Make sure you come and tune in next week for another episode where we'll do a calculation and integrate geomorphology into Mapwork. Back to you, Looney.
All right, thank you so much, Camlin, for the lesson. Mindsetters at home, thank you so much for watching and for tuning in and for talking to us on our Facebook page. Remember, guys, it's the weekend, it's like a long weekend, so enjoy the weekend, guys. Be safe, but don't forget to learn more, learn extra. Always watch our shows and everything else, and always study and prepare yourself for school and all of that. Thank you for tuning in, guys, and until next week, same time, same place, we love you. Goodbye. Mindsetters, welcome to a Thursday show with Looney and Camlin. How are you, Camlin?
Hi, Looney. Guys, geographers, welcome back. We've got an exciting episode today dealing with all your Mapwork calculations.
All
Looney?
right, that's cool. You heard it, guys. We're doing Mapwork. So I hope you guys do enjoy the show. Don't forget to hit us up on Facebook, on facebook.com/Learn Xtra, and then on Twitter @Learn Xtra. If you're asking, Looney, but why are you holding a calculator? Well, you can win yourself this calculator just by simply completing the Taste Yourself section from the notes and then filling in the entry form. But I will post all the information on our Facebook page, guys, so don't search, okay? So you can send yourself to win this Casio calculator. You can download the show notes, the videos, and the schedules on learn.mindset.co.za, or you can click on the download on our Facebook page, or if you just want to view them, especially if you have a feature phone, you can view it by clicking on the link with view. then you can view the notes. So with all that said, it's time for geography.
Guys, as Looney says, hi guys. Welcome to another exciting episode where we're going to today integrate climatology with the working of topographical maps. Today, you should be able to understand how climatology works together with Mapwork, and you should be also able to identify the integrative aspects of climate from your theory into the geography. Now, let's start off with exact position. And to do this, I'm going to call upon Looney to assist me to explain to you how we use the globe in understanding the location of position. Looney, with your help.
Okay.
So, let's grab the globe and get rid of this material here and get the globe onto the table. Now, as we've studied last week, you'll note that the Earth is geoid or spherical in shape. But I want you to zoom in onto the lines that run from east to west, as well as the lines that run from north to south. What you've learned up to this point is in your grade 10 and 11 content is the following. The lines that run from the north to the south are referred to as longitudes. The lines that run from east to west are referred to as latitudes. These are the imaginary lines which divides the Earth into hemispheres. The prime lines that you have studied at this stage is the equator, which is the 0-degree line that runs across the Earth's surface. Remember, this 0-degree line divides the Earth into a southern hemisphere and a northern hemisphere. The prime line of longitude, which is your 0-degree line of longitude, is referred to as the Greenwich meridian. The Greenwich meridian divides the Earth into a western and an eastern hemisphere. Using good examples for you to better understand these calculations. And remember, always we are integrating climatology into topographical maps. And hopefully by the end of today, you will be able to identify useful hints as well as tips in applying these skills. So guys, we've got a packed show today, and hopefully by the end of today, there are two key elements that I want you to acquire. The one is to calculate the grid reference or position on a topographical map, and the other is the integration of climatology into topographical maps. Let's get straight into it. Before we go into the discussion today, I want to go back to last week's question, which was your challenge question, and also pose this week's challenge question to you. The first question that we're asking is, what is a toposcope? Hopefully you've had the past week to ensure that you've identified what is a toposcope, which was last week's question, which we will answer at the end of the show, as well as this week's question. What is the difference between a mine dump and an excavation? So guys, go quickly to the index sheet where you've got the key on your topographical maps, and you'll be able to differentiate between what is a mine dump and what is an excavation. These are your challenge questions for this week. Hopefully by the end of this lesson, we will ensure that you get the clear answers to these questions. Graphical skills and techniques on topographical maps. Let's have a closer look at what we'll be dealing with today. In today's lesson, we will be applying the following concepts. Apply skills in map reading and orthophoto maps. We will be able to analyze these in terms of climate and climatological aspects that you have studied in theory. The next one is to examine important terms as well as explain key concepts related to the locating of position. From grade 10, you have been dealing with the locating of position, which in actual fact is the calculating of the grid reference. Today we'll be analyzing the globe and how it leads to the formation of a topographic map and showing you step by step how to calculate the grid reference, or in the case of grade 10 and 11 learners, the calculating of the location of positions. Let's look further on. We will also be developing key skills in a step-by-step process in order to calculate the position on topographical maps. Further on, we will be sampling a few questions to help you practice, which is very important in the geographical skills and techniques that you use. Whenever you are answering questions, especially dealing with the calculation aspects, ensure that you practice these calculations. And today we'll be using sphere. Now, when you study in grade 12 the location of position, it is this in mind that you should know the following. We have what we call the 0-degree equator. What you should understand is this is regarded as a low latitude. Any latitude, and if you look closely, there's lines of latitude, all your latitudes running from east to west across the globe or across the Earth's surface, right? The lines of latitude are referred to as follows. And note, they run across the globe. What you should remember is from 0 degrees, moving to the poles, we have up to 90 degrees. When we refer to 0 degrees, we refer to the low latitudes. 0 to 30 degrees are regarded as the low latitudes. From about 60 degrees, and now we're going to use South Africa as an example. Note, there's my equator. From 0 to 30 degrees is my low latitudes. From 30 to 60 is what we refer to as the mid-latitudes. What you should remember from your content is you study here your mid-latitude cyclone. And remember, from 60 to the poles, the South Pole in this example, is what we refer to as the high latitudes. So when we're looking at your hemispheres, note, what happens in the southern hemisphere also happens in the northern hemisphere. So you have your equator, which is your 0-degree line.